Okay, so I'm delighted and very excited to be here today for two reasons. Firstly, this is the first time speaking at Hack in Paris, so I'd like to thank the Hack in Paris team for the opportunity today. And secondly, I'm going to be discussing for the opportunity to demonstrate and also share with you for the first time here today a new Windows defense evasion technique which has been discovered by McAfee ATR. Who here is familiar with process manipulation such as process injection? Yeah, got a few hands. Process hollowing. Yeah. Process doppelganging. A few more. So we got a few volunteers for a demo later. Yeah, only joking. Okay, so what if we had a technique that was much simpler to execute, required no code injection, didn't require any complicated APIs, most likely affects every endpoint security solution, impacted all versions of Windows? Well, we do. And we call it process reimaging. And that's what we're going to demonstrate here today. And we're also going to talk about some of the mitigations and how you can protect yourself. So if you cast your minds back to April, May 2018, does that resonate with anybody from a ransomware perspective? So it was roughly 5 months after process doppelganging was disclosed at Black Hat, it became weaponized with Synack ransomware. At that time, myself and an ATR teammate, Eamon Ryan, were analyzing Synack ransomware in the lab. And what we discovered was it was using process doppelganging, but if you blocked doppelganging, it would fall back to process hollowing. Okay, so at this point, you may be asking, well, what is the relevance and what is the importance here today? And why does it matter, process reimaging? Well, if process doppelganging was weaponized only 5 months after being disclosed, there's a high likelihood this is going to be weaponized also. And I think you're really all going to be amazed how simple this is to execute. Albeit pretty complicated under the hood, and we go through some of the kernel drivers or the kernel APIs and how it works, but it is relatively simple to execute. So later on, we're going to do a live demo, and we're going to show how we can bypass Windows Defender with process reimaging. The reason we use Windows Defender is because process reimaging impacts all versions of Windows, and Windows Defender is the default security solution on Windows. Now, I just want to clarify before we get into the presentation. When we speak about Windows Defender, it's explicitly in relation to process reimaging. We're making no reference to Windows Defender's ability to detect or protect against process hollowing or process doppelganging. So before we kind of get into the detail, I'd like to get some attribution done. So myself, I did all the reverse engineering, understand what was actually happening under the hood, root cause, and also the impact and the technical analysis. And then Steve Herndon, who was one of our kernel developers, he did some of the proof of concept code, and he also designed a fix for this. And Cedric Cochin, who maybe a lot of people here today know, he's a Parisian living in Hillsborough in Portland. Cedric actually discovered the technique and how to execute it. And then Steve Pavolny, who's the head of vulnerability research for McAfee ATR, or Advanced Threat Research. Steve handled all the communications and the disclosure process. So just a little bit about myself and who I am. So I go by the name W3Night on Twitter, probably connected with a few people here. I've been working in technology for about 20 years or so. The first 10 years, I worked as an electronic engineer across the semiconductor and also across the medical device industry. And during that time, I worked across hardware and software. And then about 10 years ago, I moved into security. And since then, I've worked across product security, IT security, as an individual contributor, team lead, and a manager. And that's given me kind of really good perspective before moving into a security research role within McAfee ATR. So over the next 40 minutes or so, we're going to discuss an overview of what process reimaging is. Then we'll talk about the AV scanners and how they relate to process reimaging. We'll talk about the MITRE ATT&CK framework and defense evasion. And then, hypothetically, what would process reimaging look like if it was weaponized by Synack ransomware? And then we'll get into a bit more detail under the hood, what's happening with the kernel APIs that are exposed by NTDLL, and why this is actually happening, and why we can do this technique. And then we will finish off with a live demo. Demo gods permitting, but hopefully that all goes well, and I'm sure it will. And I think you'll really see how simple this technique is, but very impactful. And then we'll finish up with some impact and protection mitigations. So Microsoft did give an update for this in the June cumulative update. but it only resolves a small piece of this bypass, and it only it mitigates it for Windows Defender. It doesn't fix it at the operating system level. So we'll talk about that later on. So to give an overview of what process reimaging is exactly, it's exactly what the name says. It takes a process and it reimages it, and associates the process with a different file on disk. And if you think about an endpoint security solution, why does that matter? Well, there's generally two use cases where an operating system will depend, or sorry, an endpoint security solution will depend on an operating system. It will depend on it to verify whether an executing process has any malicious files associated with it on disk, but it may also look to verify whether that process can be trusted. If it's signed by, for example, Microsoft, or wherever the case may be, and it's trusted to call into its infrastructure. So they're generally the two use cases. Now, I do want to highlight here as well that process reimaging targets non-EDR type security solutions. So with EDR type solutions, if they're configured correctly, they can trace processes and can detect this. So this would target specifically consumers and people who do not have EDR, such as small, medium enterprises. As I mentioned, it's equivalent in impact to process hollowing and process doppelganging. And it's highly likely that every endpoint security solution is vulnerable to this, because they're going to be dependent on these APIs. Okay. One last thing I wanted to say on this is that what's really important here is that once this process gets executing and we reimage it, then until there's a signature update, or even after a signature update, you need to do a full scan or a reboot to detect this. So we talk about AV scanners. So on the left-hand side here, you can see this is the general flow for a process getting created on Windows. And when an AV engine is active, it will scan a file for malicious code at file create, at section create, and image load. Once it has a signature, it will detect a malicious file. Now, if it doesn't have a signature, it will not detect at those points. And at that stage, the process will execute, and then the endpoint security solution becomes dependent on the operating system APIs to verify the attributes of that process. And what I mean by the attributes is that whether that process has malicious files and disk associated with it. Sorry. So just to define process reimaging exactly what it is. So the Windows kernel APIs return stale and inconsistent file object paths, which enable an adversary to bypass Windows operating system process attribute verification. And right now, there's actually no documented way to securely identify the files associated with a process on disk in Windows. So when we talk about the MITRE ATT&CK framework and the different domains within it, the MITRE ATT&CK framework is a post-exploitation enumeration techniques which are used by real-world adversaries on Windows, Linux, and Mac. And once an adversary gets code execution on the box, they'll obviously want to evade detection using defensive evasion techniques such as process hollowing and doppelganging, and now process reimaging. Do we have any Game of Thrones fans here today? Yeah. Everybody happy with the last season? Or maybe I shouldn't ask that question. But everybody trust this guy here? Yeah. So he's Irish, but I still don't trust him. So Sansa depended on this guy and she trusted him, but she wasn't completely blind to him, right? And any Game of Thrones fans know how that ended up in the finish. The reason I show this is because I've mentored a lot of product engineers and security engineers, and one of the first things I always say, when you're looking at a system, you got to understand the security model. How does it work? What are the main dependencies? How can you break that system? What does it really depend on that may be in or out of your control? And if you think about if you think about the endpoint security solutions, sorry, just wrong button there. If you think about the endpoint security solutions, they place inherent trust in the operating system for capabilities such as digital signature verification and also for process attribute verification. So some time back, the team at SpectreOps subverted the Windows operating system for digital signature verification. And similarly, what we've done in ATR is we now subvert the operating system for process attribute verification with process reimaging. So just to cast our minds back again, I'm going to go back to May 2018 and talk about use Synack ransomware as a case study. And the reason I'm going to do that is because we're going to compare and contrast to set ourselves up for understanding the demo of what hollowing and doppelganging look like compared to process reimaging. So when we look at a typical ransomware, generally, it needs some initial, or I suppose any attack, but in particular for SYNAC ransomware, it generally needs some kind of infection vector or initial access, such as a drive-by compromise or a phishing attack. And then it needs to get code execution. Once it gets code execution, then it's going to try and evade itself from the operating system, from the endpoint security solution, from detection. Now, if you look at how process doppelganging worked, it had a dropper, for argument's sake, we'll call it synac.exe, and then it had a trusted binary called MSI exec. Now, for process hollowing, as I'm sure a lot of people know here today, it starts off by creating the process in suspended mode. So it uses the trusted process MSI exec, and then it uses numerous APIs whereby it hollows out the memory and then replaces it with malicious code. Now, if the endpoint security solution fails to detect this dropper, then the process is allowed to execute. Signatures get updated, but once the process is executing, then it's reliant on its operating system to tell it information or attributes about that process. And so this is where process reimaging comes in and why these APIs are important. Because you now have 4 APIs, which we'll look at in a moment, which are required, which the endpoint security solution depends on to give it information about the running process. And so the operating system now gets MSI exec back, which we expect right with process hollowing. We know how that technique works. And now the adversary is free to act on their objectives because that's a trusted process. Now, if we talk about process doppelganging, same approach here, exactly the same binaries being used, albeit a little different the technique. It also starts with a trusted process, MSI exec. And then it uses the Windows transactional file APIs. A little bit different to process hollowing, but the same end goal and impact, where it can get malicious code executing in a trusted process. And once again, once the endpoint security solution fails to detect that dropper, then the operating system will return back and say it's MSI executing and it's trusted. And once again, the adversary is free to act on their objectives. So let's compare and contrast what they look like with process reimaging. So process reimaging has the exact same prerequisites as process hollowing or doppelganging. You need to have code execution on the box first, and then it's about evading detection. So they've already gained access to the machine and they've got code execution. Now there's 3 attack vectors or variants to process reimaging, and we'll see this later when we look under the hood, and also when we see the demo live. But there's a file path where it's as simple as renaming the file path of the process that's executing, or the second one you rename the file name, and then the third one can use either the file name or file path, but it just uses load library to reuse the same object in memory. It's not as impactful, but we will just highlight it here today. It is a variant of it, but it still requires the change to file name or file path. Okay, so what would SYNAC ransomware look like if it had weaponized process reimaging? And the reason this is so important, if you think about defense evasion techniques, right? There's many techniques in the MITRE ATT&CK framework. And with SYNAC, we saw process doppelganging and hollowing being used together, right? They're not just using one technique anymore, they're using many techniques. So this is another bow to their arrow in a way, and we need to make sure we're protected against this. So we'll just go through how the mechanics of this attack would work, or this technique. So it's a little bit different. So instead of starting with a trusted process, it starts with a malicious exe. So if you think about what would happen here is, same as before, you have the same 2 files here, but we have an additional undetected file here that's dropped the disk. Now, instead of having numerous APIs here, noisy APIs that can potentially be detected by Yara, what we have are very, very simple APIs, which would be very hard to detect with Yara because they would be very noisy. It would be seen typically in a binary, and they're used to copy and move a file around on the file system. And then once the endpoint security solution fails to detect the dropper, we get that malicious process executing. They update their signatures, and then they query the operating system APIs for the executing process name. And you can see here, right, there's a malicious process executing. We don't detect it, right? the operating system gives the wrong information back. What we actually see from an operating system perspective is MSI exec. And we'll actually see that in the demo. We'll see the malicious process executing, and then when we reimage it, you'll actually see the operating system gets a different view of it. So we get the exact same impact as process hollowing or doppelganging. And once again, they're free to act on their objectives. So we'll go a little bit deeper now on the kernel APIs and what's actually happening under the hood and the reason for this. So there's numerous APIs involved here. We'll see a summary table in a moment, but there's 4 particular APIs. The first 3 APIs here, we have get module file name, we have process image file name, and we have query full process image file name. And ultimately, they all call into the Windows kernel query information process, which is exposed by NTDLL. And ultimately, that goes into the Windows kernel, which is like a switch table, a large switch table, and gives you back, depending on the API you call, it will give you back information from the eProcess structure. Okay? Now, the reason process reimaging can actually happen, this technique, is because Windows is inconsistent, right? Once we reimage the process, these fields hold different values for the file name and file path. Once you rename them on a disk, you get inconsistent values back here, and depending on the API you call, you will get the wrong file name or file path. So at a very high level, that's what's happening. So we have these 3 APIs calling into query information process, and then they get information back from the eProcess structure from different fields depending on the API you call. And the 4th API is get map file name. And this API calls into another NTDLL API, which is called NT-query virtual memory. And that gets this information from the eProcess structure, the VAD, or virtual address descriptor. Okay, so they're the 4 APIs, and at a high level, 10,000 foot level, that's kind of what we're seeing in IDA, what's actually happening underneath. Okay, so to summarize that, on the left-hand side here, we have 4 APIs. The specific APIs are get module file name, get map file name, get process image file name, and query full process image file name. And depending on which API you call, once you reimage a process, every version of Windows will give you back the wrong file path if you rename the file path. But any version less than Windows 10, depending on which one you use, will give you the wrong file name. Okay, and one thing to note here is, sorry if I just go back one slide, on Windows 10, a new field was added to the eProcess structure, and it's the image file pointer field. So in Windows 10, if you call the right API, this field here will always give you the right file name when you rename it. But for some reason, Windows Defender does not use it. So even though they have the capability in Windows 10, they don't use it. And they get the wrong file name back. So we'll see more on that later. So as I said, this is a summary table. And you can see here what we summarize is the APIs, the NTDLL API they call, and then the offset fields within the eProcess structure, whether they get the file name or file path. And you can see here on Windows 10, depending on if you use these 3 APIs, you always get the right file name, but you'll always get the wrong file path. So we said there was 3 kind of variants or attack vectors. There's the file path, the file name, and you have the load library version. So I'm going to show now what's happening at the kernel level, and then we'll see in parallel what's happening at the process and file system level. So as you can see here, what we said before, we have 4 APIs. And then, depending on the API that's called, they will call into NT-query information process or NT-query virtual memory. Now, these 2 top APIs here, when you put a kernel debugger on these, you will see they pass these values in 2B hex, which executes switch case 43 in the kernel once you call query information process. And then they get the file path and file name from the SE audit, from the section object. Now, if you call get process image file name, which we'll see later that Windows Defender is doing, it executes a different switch statement within the kernel, and it gets the information from the section object here. And then the get map file name, it actually gets it from the VAD here. So all these fields are within the eProcess structure, but depending whether your process has been reimaged or not, which we'll see later, these will actually give you inconsistent results. So this is the data structure side, and this is the logic flow here. And how did the user mode APIs connect to the kernel APIs and then to the actual eProcess structure. So if we want to talk through the sequence of actually what happens from creating a process, what happens on disk, and then what's happening at the kernel level. So we will see in the demo later on that ultimately what we do is we just create a process called running phase1.exe. And so the directory running, you can make that any directory you want, and we just call it phase1.exe. That can be any exe you want. But that exe is Mimikatz. We just renamed it. So from the talk earlier today, I'm sure everybody remembers what Mimikatz is. It's a post-exploitation tool, and most endpoint security solutions should detect that. And that's the reason we're using it. And we will see Defender detected, and then once the image has been, our process has been re-imaged, it will fail to detect it. So what we do then is we just simply rename the execution directory. So we launched our process as running phase 1, which is ultimately Mimikatz. And then we rename the path to hide running. So now what we have is, and then we copied a good exe, which is MSI exec, which you saw with the Synac ransomware being dropped to disk. And we copied that to phase1.exe. So ultimately what we have now is we created a process with a malicious file. We renamed the directory, and then we copied a good file to where that malicious file was. So now when you scan that with Windows Defender, what happens is Windows Defender calls the API, get process image file name, and it actually returns running phase 1. And running phase 1 is now MSI exec.exe. And we will see that in Process Explorer with the demo later on. So ultimately, you have Mimikatz running as phase1.exe, you've renamed the location, and now Windows Defender thinks MSI exec is executing. And you can see here there's been absolutely no changes here in any of the fields in the eProcess structure. So the Windows kernel has failed to reflect the file system changes through the file control block to the eProcess fields. So that impacts all versions of Windows. So you simply rename the directory, and you can completely bypass the process attribute verification. So for Windows 10, the second variant is called file name changes. So instead of renaming the file directory, we just simply rename the file. So you can see here again, apologies. You can see here again, we launched our process running phase 1, which is Mimikatz. And then instead of renaming the directory, we just renamed the file name. So we renamed the file to hidden.exe, and then we copied MSI exec, which is good exe, to phase1.exe. And then when Windows Defender runs, once again it calls the same API, and it detects phase 1, not hidden.exe. So once again it gets the wrong file on disk once you rename the file. But you can actually see, as I mentioned before, Windows did put an update into Windows 10 for a new field called image file pointer, which actually does get the right file. You can see here it reflects the change. So you change the name on disk and it does reflect it, but depends on the API you call to give it the right value back. But the API that Windows Defender is using does not reference this field. It actually references section object, and so it gets the wrong file on disk. So that's for versions greater than Windows 10. And the reason that's happening with the file image pointer, if you look in the kernel, the file image pointer is located at 448 hex offset in the eProcess structure. And now I'm not sure, that field was added for Windows 10. I'm not sure why they're not using it. It obviously does reflect the file name changes, and you can see the changes clearly in the kernel, but it's not being used. Now for Windows versions less than 10, what we have is, it's a little bit different. So, and what I mean by bit different is that it makes different changes here in the eProcess structure. It doesn't have the image file pointer, because that's only for Windows versions 10. So once again, you rename the file name, you copy the MSI exec, the good file, to phase1.exe, and then Windows Defender fails to detect the Mimikatz process executing. And you can see why, right? I mean, the only field that's updated here is the VAD, right? So the only API that would give you the correct file name is getMap file name, which Windows Defender is not using to verify the backing file or disk associated with a process. Everybody with me so far? Yeah? I know there's a lot in that, but when we do the demo, it'll solidify it and you really see what's happening. So once again here, like we don't have the 448 offset here. We have the P reference process file pointer, which points to the section object. And obviously we're getting the wrong information back. I'm not going to go into these ones in too much detail. They're a slight variant, they're not as impactful. They only impact the get map file name. And ultimately, what's happening here is when you do a load library and a free library, it seems to cache the object and the file path associated with that file object. So then when you reload it a second time, it uses the incorrect path. So I'm not going to go into it in too much detail because it still depends on the file name and file path, but it is a variant of it, and it impacts all versions of Windows. So I think I want to spend a bit of time in this demo and really kind of solidify this here today and put a lot of this into action so you can see what's happening. So in the demo, we're going to focus completely on the file path. We're not going to do the file name because even with the latest Windows update, for the June cumulative update, this still works. If we did the file name bypass, it wouldn't work because Windows protected against it specifically for Defender, not at the OS level. Okay, so we're going to fire up this demo and show exactly how this works. Second. Okay. Everybody see that okay? Just duplicate my laptop. So we've Windows Defender turned off here. The reason we have this turned off is we're simulating an undetected piece of malware being dropped to disk, right? We're not in the habit of releasing 0 days here, so we're just simulating what would happen in a real world scenario where, for example, with Synac, you got a binary which was dropped to disk, a malicious binary, and wasn't detected. So let me just show you what's happening here. So what we have in this excluded folder is bad.exe, which is Mimikatz. You can see here, it's Mimikatz. And then we have good.exe, which is MSI exec. So we're just going to talk through exactly the flow we saw earlier, and then we're going to execute it. So you can see it's MSI exec. Now, on this run here, we're not going to reimage the process. All we're simply going to do here is create a folder called running, copy Mimikatz to phase1.exe and execute it. So basically, we have Mimikatz running as a process called phase1.exe, and Defender should detect it. Okay, so we're just going to show what it looks like when you don't reimage the process. And if you look at the filter here for process monitor, we have a filter on running phase1.exe. So what we see is when Windows Defender scan runs, it will actually look at this location correctly for the file on disk. And then when we show the image process later, you'll see it looks in the wrong location. So let's just run this and see what happens. Sorry, just there's a couple of events on process monitor. So our filter is on Windows Defender exe and on the path where we're running phase1.exe, which is ultimately Mimikatz. So process reimaging underscore file path.exe is basically just simulating a dropper, which would be used, for example, with Synac. And node stealth just means that we're not actually going to reimage the process. So you can see here, we've Windows Defender turned off because we want to simulate an undetected binary, let the process run, then we re-enable Defender and it should catch it. Okay, so you can see Mimikatz is running there, right? Now if we pick up Process Explorer, any second now, okay. You can see our unsigned dropper has launched phase1.exe, which you can see is Mimikatz. Can everybody see that clearly? Yeah? Okay. So let's run Windows Defender. So you can see already Windows Defender has picked something up here. There may be threats in your device. And you can see the alert here. And that's what we'd expect, right? We have a malicious process running. It's phase1.exe. You can see here, we just copied Mimikatz in here and called phase1.exe. That's all we did. And that's exactly what you'd expect, right? So there's no reimaging going on there. And you can see here it detected Mimikatz. Okay? So let's just pause that and we'll go and do the process reimaging. So now with process reimaging, exactly the same setup. We have Windows Defender disabled, simulate the undetected binary on disk. We have our dropper, and then we have Mimikatz, and we have MSI exec, just called good.exe, as I said before. So what's going to happen this time, and I'll leave this window open so you can see it happening real time. We're going to create a directory called running, which will have phase1.exe as before, and that will also be Mimikatz. But then we'll have a second folder. We'll rename that folder called hide running, and then we'll make another folder called running, which will have the good.exe, and we'll completely subvert the operating system. So what I have here is I have a filter on the Windows Defender process. I have a filter on running phase1, and I have a filter also on hide running phase1. Now the reason I put two filters is because you'll be able to see the binary I used to launch the process will be located at hide running, but Windows Defender never even goes to that location. And our good.exe is going to be at running phase1.exe. So it completely looks in the wrong direction, or wrong location, and it trusts the file on disk. So we'll just hit OK there. Okay, so you'll see the changes happening here real time. So we started, it's just running there, it's phase1.exe, that's Mimikatz, and now we'll rename the directory. You'll see it happening now. So now we just renamed running to hide running, and then we create a new directory called running and put the good.exe in there. So the process path you started with now has a good file as opposed to the Mimikatz file. So now let's have a look in Process Explorer to see what's happening before and after we run Windows Defender. So now you can see here, that's exactly the same. We started with Mimikatz, we've reimaged the process, and now you can clearly see that's a trusted Microsoft Windows installer. That's MSI exec. So now we have Mimikatz running, and from an operating system perspective, it's MSI exec. And that's process reimaging. And what we'll do here now is we'll just run Windows Defender, and you'll see it fails to detect it. So, 1 second. So now you can see Windows has looked in the same location, running phase1.exe, but we've renamed that exe to MSI exec. And our malicious file is running in hide running location. So you can see there's no alerts there. And I'll leave that running. We can check at the end of the presentation. You'll see it doesn't detect anything. So you can see it's already looked in that location. It's looked at this executing process. It's looked for the associated file on disk. And the file on disk you get is MSI exec as opposed to Mimikatz. It's completely bypassed the operating system APIs. So I'll leave that running, and we'll see at the end that it comes back with a clean scan. Anybody any questions on that? Okay, so I'll just continue on with the presentation, and we come back to that in a moment to see a clean scan. Okay, so that's the demo. Just to give a summary then of the process manipulation techniques, a recap. So we have process reimaging, a lot easier to execute, very, very simple. You can see there all we're doing is renaming a directory or a file name, that's it. There's no complex APIs or code injection involved. Excuse me. Process hollowing and process doppelganging. The difference is they start with a trusted exe, we start with a malicious exe. But ultimately the end impact is the same. They both appear as trusted processes and are allowed to evade detection and execute and dwell on the endpoint. So just to there are some pros and cons, right, to all the different techniques. From a process reimaging perspective, as I said, it's a lot easier to execute. It doesn't require code injection. Impacts all versions of Windows. There's no real API signature there from a Yara perspective, and there's no protection out there right now. Now, I suppose on a disadvantage side is you can't use it as a fileless attack, and you can't delete the file on disk once you have the process running, like process hollowing and doppelganging. You still need the malicious file on disk because it's still associated with the process. You can't delete it. Now, we'll talk about a fix that we put in ourselves, which was designed by Steve Herndon. But ultimately, if you're using EDR or memory scanning, obviously you would detect this. But for non-EDR systems, you're not going to detect this. So from an impact perspective, as I said before, there's 2 use cases. And we scored this the same as we did process doppelganging. We gave it a CVSS of 5.0, where the integrity was very high because you cannot no longer trust the process. So the 2 use cases we spoke about earlier is where you're trying to verify a remote process, whether you can trust the file associated with that on disk. And obviously you can't in this case. And then the second one is where you're trying to verify the actual trust of the process, whether that can call into your trusted infrastructure or not. Now that, depending on your endpoint security solution and the architecture, how it works, that CVSS could be a lot higher. I can't quantify that because it depends on the endpoint security architecture. So if you have an endpoint security solution and you're using any of those APIs mentioned today, it's highly likely you're vulnerable to process reimaging. So from a protection recommendations to the endpoint security vendors, what we say is that you need to track the file object. So if you remember back to the process creation steps of file create, you can get an idea at that step when the file object is created, before it's cleaned up and it's closed by the operating system. And you need to track that ID the whole way through, keep that cached. And then when you want to verify a process, you take the trust away from the operating system and you use that ID yourself to verify if the process has been reimaged or not. So the endpoint security vendor actually needs to track this unless Windows go and update the operating system. I mean, I think that's the right thing to do. Windows haven't done that, and Microsoft, I hope they do it, but right now they haven't. So we did give a number of protection recommendations to Microsoft as well. So for example, one of the things was that if you change something in the file system, that the file control block will reflect that in the process structure in the kernel. And also, one of the big things is to consolidate the APIs, right? We have 4 APIs effectively doing the same thing and getting information from different areas in the kernel. They're inconsistent, right? It needs to be more consistent. So Microsoft did make an update in the June cumulative update, as I said, but it's only a partial fix for the file name bypass, and it only mitigates Windows Defender. There was no change at the operating system level. Okay, so if you're an endpoint security solution, you know, I'm hoping Microsoft will update it at an operating system level, but if not, you're going to have to do, I think the recommendation that we propose is the right way to do that. So Windows Defender, as I showed today, that's the latest updated operating system version, is still vulnerable to the file path renaming. So even with their patch, they're still vulnerable. And that's it, right? Sinead Dina, which is Irish for that's all, folks. And we have a blog which will be released after this, which goes through this in detail. And I'm sure you can all decode that piece at the end. I'll leave that for a challenge for everybody, which I'm sure won't be much of a challenge, but you can decode that nonetheless. So thank you for your time today. And if there's any questions, I think we have another 3 minutes or so.